Okay, so we now know how we can take a derivative of a function of other functions. So if we recall where we were earlier, we can always write down our weak form of our differential equation as a residual. And the residual is going to be some function of this variable we want to solve for, which in our Berg's equation was un plus 1, it's the next state, but it's the variable we want to solve for. And we might be nonlinear in that variable. And the test function, and we're always linear in the test function. And so we're trying to solve for this being 0, and we've just worked out how to take a derivative so that we know what the definition of df is, and df has now 3 arguments. It has the original state, so this is now the point in this space, in U space, at which we are taking the derivative. It still has v, whatever value of v we choose to take, and in fact we choose to take all the basis functions of v all the time. And it's still, but it now has u, and u is, in some sense, the direction in which we're taking the derivative. Now, u is obviously a function in this function space. So you can think of u as being the perturbation function that is the direction in which we're taking the derivative. So we can ask ourselves, if I have a function and now I have some function of that function, right? That's what f means. So then what we're asking is, how does this function change if I add a little bit of another function? So a little bit of another function might be that I bump it a bit here, or it might be that I move the whole thing by a little bit. But it's an infinitesimal, right? The direction can be the function given the direction can be as big as you like, because we're adding a tiny little multiple of that function on, the limit as that goes to 0. So that's what the gradient means here. So now, in order to get Newton's method back, what we want to do is we want to write out the Taylor series. And so what that means is that we are looking for u plus, well, we might as well just call this u tilde. It's going to be the same thing, right? Right, so what we're saying is, if I start here and I move by this much, what is this function going to be equal to? And we can do a Taylor series. So we can say, okay, well, the first approximation is that changing this function doesn't change f. So the first approximation is that that's just the same as evaluating f where I started. And then the next best approximation is you say, okay, if I change this by sorry, I need to put in a size here, right? How far we're going. So if I put in, if I move by h much of this in this direction, then we'll just assume that f is linear in u and move by that much. So what that means, that's equal to h times right, remember this is the change in u in the direction of u tilde. So that is one of those, and I can keep going. Right? I can take the second derivative in that direction and so on and keep going out there. And what I've done is I've written out a Taylor series. Now the Taylor series, these things keep getting higher and higher rank, right? So in order to evaluate this one, I have to choose 2 functions, u and v. In order to evaluate this one, I have to choose 3 functions, u, v, and u tilde. and so on. So the Taylor expansions for the, multi-dimensional functions get big. But that's fine because we were going to stop at 2. Right? We're doing Newton's method. We're going to stop here. So what have I got? I've got, this is now an approximation. So why did I do that? I did that because I want to know from where I am, how do I shove my function, how do I change my function so that this thing comes out to be 0? Right, that was the objective of the exercise. We want to solve the equation. We want this to be 0. So what do? We set that to 0. And I've written something slightly wrong on the previous slide. That's fine. I just have to work this out. So we have to ask ourselves here, where is h? So as I've written this now, we're good. This is, actually, everything I've written so far is correct. H is a number. But now what we're going to do is we're going to do this for all v in the basis function. Right? All v in the all basis functions of v. So this is now going to be by I. So I'm now going to expand this out into a set of linear equations. Right? So I need to solve this not just for one particular v that I choose, but I have to solve it for all of them. And as we previously showed, to solve it for all of them, it's sufficient to solve it for all I. But now this is a whole load of different equations. There's no reason to suspect that that is the same in each case, right? So I'm going to get a vector of HIs that comes out to be this. So now, we have to ask ourselves, so what are these things? So remember now, we've chosen the point U. U is the fixed point from which we're working out our new update. We haven't chosen this one. So, if I run this, try to see if I've written this out right. So now, yeah, that's right. The H, yeah, H. So this guy here is actually U tilde J by J. Yep. And the important rule here is that this is linear, right? The derivative is linear in these arguments, not this one, but these ones. So that means this comes outside. So this thing, so we'll just rearrange over to the to this the right way around. H df U phi I phi j U tilde j that is equal to, that's an HI, which I should put on this side to make this clear, minus F at U phi I. Now this guy is a matrix. Right, it's a matrix which is hitting this thing. Actually, I don't need this. So because uj can be of any size I like, I didn't actually need that. Right, sorry, that was my mistake. Just need a perturbation tilde. It scales by the perturbation. So my failure to do calculus correctly. So the entries of this matrix are given by choosing one I and one j. Right? So this matrix, which we'll call J because it's the Jacobian, it is actually the same concept as the other Jacobians we see. Jij, the ijth entry in J, that's equal to D I don't need that. And now, and this thing over here, that's a vector for the same reason, right? So there's one fixed point here. So each phi I choose, I get a number. So I get a complete set of things over here. And so what we've got is J U tilde equals F, where F is the vector that I've got from there. So now I solve. So I say that U tilde equals J inverse F minus J inverse F. And to get the Newton method, I just go back to say that U new or U next equals U old plus minus. And iterate on that. Now there's a subtle trap here. If we're in a time stepping equation, it's important to realize that these are not time steps. Right? At one time step, we've got un plus 1 that we're solving for. And then we have a series of guesses for what un plus 1 is, which we solve for with the Newton iteration. When we're done, then that's un plus 1. And then we step forward in time again, which is a completely separate operation. So this is not time stepping, even though it sort of looks like it, right? We keep getting new values. These are just iterative guesses at this problem. And it should be pointed out here that there is nothing amazingly unique about the Newton method. The Newton method is sort of the base member of a whole class of methods. But the important point here is that what you need to do for this big class of nonlinear methods is you need to be able to do exactly this. Whatever your function is, you need to be able to evaluate the function at any point we choose, and you need to be able to evaluate its derivative at any point we choose, its Jacobian at any point we choose. And so it's sufficient to get access to all these nonlinear solvers and be able to solve really rather arbitrary sets of nonlinear equations that we are able to get these, it's efficient that we are able to do this, to evaluate these two things. And so when you work with software tools that do this for you, so in particular, a bunch of the software that we work with uses PETSI. And PETSI is a big solver library, and it's kind of most famous, I guess, for its linear solvers, but it has a nonlinear solver facility as well. And in order to use the nonlinear solver facility, what you do is you provide callbacks, and those callbacks are a callback to do this and a callback to do that. And what happens is PETSI passes you a state vector, and you respectively give it back the vector of the residual or the vector of the Jacobian. And that's what's going on back there under the hood. The other thing I promised I'd do, so we're not going to dive in and do boundary conditions today because we've got 20 minutes to go and it will take us too long. But what I would like to do is to look very briefly at the reverse operation, because that turns up in a few contexts as well. So if we have an operator Jij, which is something like this. So what does that mean? It means that we've got some function, and the function might have, someone should have screamed at me that I've been forgetting my colons. And the function might have some known values, and it might be nonlinear in those known values. But then there are two arbitrary values, right, which are effectively now vectors. And it's linear in those vectors. So that means that the function is equivalent to a matrix. That's a really fundamental property of linear operators, is that they are equivalent to linear algebra objects. So a function of two linear variables is equivalent to a matrix, and a function of one linear function is equivalent to a vector. And so sometimes that's a wonderfully convenient thing to do, because what's going to happen inside the linear solver, inside here, is I'm going to evaluate this function lots of times for lots of different values j. Right? I'm going to evaluate the matrix vector product. And a convenient and sometimes cheap way of doing that is to build the matrix and keep doing the matrix vector product. But there's another way. The other way is what's known as the matrix-free approach. And under the matrix-free approach, I don't ever build this matrix. What I do instead is I keep around this function. And then every time someone asks me, please compute JB, where J is my matrix and B is my vector, I say, yes, but J is really what I got from evaluating this function at all the basis points of J, at all the basis functions of J, and B is really a set of coefficients for basis functions J. So what I can do is I can back out what the function was, and backing out what the function was is easy, right? So the function here is just bi phi I, right? That's what our function evaluate expansions mean. And so now I just, instead of evaluating that matrix vector product, I evaluate df u phi I b. And so now this thing has two things which I know. and one thing which I don't, and so I get a vector. I evaluate that once for each basis function, this, and I get a vector out. And so there are a number of reasons why you might do that. Reason number one, and one of the original reasons why this was done, is because you can't afford to store the matrix. So this is particularly true in like really huge seismic inversion problems. So when people are doing inverse wave problems to work out where the oil is, more or less. So you set off explosions, you look at the echoes, and you back out what the ground looks like underground. And that's a big inverse modeling problem. And the matrix is so big that they can't afford to store it. So they do it matrix free. So that's one reason you might do it. There's some more contemporary and modern reasons. And one of the more contemporary and modern reasons is that the reason for stashing this in here is because you probably did a lot of operations to evaluate this function. And so if you are operation poor, then effectively what the matrix is a cache of the results of this operation. And so what you do is you evaluate this guy, and you shove it once, and you store the results, and you use the results again and again and again. Actually, the number of results in here can easily be quite a lot bigger than the inputs to this. Right, the inputs to this are your state U, and because we have spatial derivatives and the integrals in there, a coordinate field x. There can easily be more numbers in the non-zeros of this matrix than there are in here. And so if your limiting factor is not floating point operations but bandwidth, then it can actually be faster to do matrix free, because evaluating this moves less data than loading this thing from memory in order to do the matrix X multiply. There is a downside, and the downside is if you know anything about preconditioners, which we're not going to go into here. So using the basic solver operations, so conjugate gradient, GM-res, all of those iterative solver methods only requires you to evaluate the function. Some of the preconditioners require you to look inside the matrix. So that's more of a problem. So that's a reason why you might not do it. So there's fighting back the other way. And you might also be interested in matrix free because it relieves you of the need to have a complicated matrix library somewhere. And that's a current issue for GPUs because multi-GPU linear algebra libraries are a little bit scarce at the moment. And so one other answer as to why you might do this is because it's less complicated to evaluate this guy. So that's that part of that story. I think then the best way to explain how that worked is actually just to expand that out. So let's look at that again, right? So when we go way back, so let's just use our simple equation. And so in this case, we don't even need to take the derivative, right? So in this case, we can already say that this thing over here, what we do is we say, well, that is equal to uj integral grad phi j dot grad phi I dx bi equals the integral phi I that's just expanding out the properties. This should be becoming really familiar to you by now at this stage of the course. And so then we say, and that's true for all V in V. So that means that this is true for all Vi in R. Right, I can choose any coefficients I like. So that means that it also has to be true when I take that off, right? It's true for all basis functions, and it's sufficient that it's true for all basis functions. And we showed that on a previous occasion. And so what we were doing is previously we were saying, okay, so what that thing is Mij is equal to evaluating this integral. And so then, and that produces then one number for each choice in I and J. So that gives me a big grid. And it's a sparse matrix, and the reason it's a sparse matrix is because unless these two basis functions are non-zero on the same element, this will be zero. That falls out. So the matrix-free approach to this is to say, yes, but what I wanted to do at any given time was evaluate the mass times something. And so evaluating the mass times something is equivalent to substituting that thing in here. And the terminology that's used, so this thing is a bilinear form, right? It's a function which is linear in two arguments. And if I have a form, f, which takes two arguments, A and B, probably get off using these two ones here, and I, instead of expanding it out and expanding this here, I want to replace for the unknown argument B a known function which we might call f. We've used f, what am I going to use? G. So G is in B. It's a known function, and I want to evaluate here. The operator that I use, and this is something that will be useful to you in understanding how some of the UFL stuff works. The operator that I use is action. So what action? So action that means, so this is a kind of so basically what's going on here is this is the partial evaluation of f with respect to its last argument. So the result of this is where A is now still an unknown. I haven't said what the value of that variable is, but G is now fixed. And so what all this is doing is going from a function of two arguments to a function of one argument. And because it's a linear function, that's equivalent to saying we're going from a matrix to a vector. Cool. For an almost record and unique occasion in this course, I might actually stop early. I'm normally running about 10 minutes over. And what we'll do is, having run through the nonlinear solver stuff today, that means that we're in a position where next time, which will be in 2 weeks because I'm in the US next week, we can actually do boundary conditions and understand how boundary conditions work. And depending on what people pester me to do, that may or may not be the last one. Do that then. Okay, we can probably stop now.